Blackman here from Caltech. Well, he's going to talk now, but if you want to speak to him later in general, it will be this afternoon or for the rest of the afternoon up in this office, or the lunch with cookies. Yeah, so Jonathan is a final year graduate student in the Statistics and Relativity group at Caltech, and will be telling us today about surrogate models of gravitational waveforms.
Thank you, and thanks very much for having me here. So I'm going to first go through the motivation for this talk and talk a little bit about binary black holes and the recent detection of gravitational waves from binary black holes. Then I'll discuss what a surrogate model is and why we're trying to build it, and go through a quick example with a simple toy problem so we can all follow along the steps of building a surrogate model. And then I'll discuss two particular examples of surrogate models we built for numerical relativity waveforms. So the motivation is that LIGO has detected gravitational waves from binary black holes. There would still be motivation had this detection not happened, because we would expect future detections. And we still do expect future detections, and we expect to get many more detections. And eventually we'll get louder detections. So for this particular detection, I'm sure you've all seen this figure before. It was in the discovery paper. On the top, we have the data that was observed in the two detectors, Hanford and Livingston. This plot here shows a numerical relativity waveform where Einstein's equations were solved on computers to determine a prediction from general relativity. And you can see they agree quite well with each other. And if you subtract one from the other, you get residuals that are consistent with the detector noise. So the signal was consistent with the general relativity prediction for two black holes merging. So as I mentioned, we should see many more similar events in the near future. We can measure the masses of the black holes that were involved in this merger and potentially measure something about their spins. So we can do astrophysics that way. We can also test general relativity by making sure these signals match predictions from general relativity. And as the signals get louder, we can do better measurements of the masses and have better tests of general relativity. So the parameter space of these binary black hole systems is 8-dimensional in terms of its intrinsic parameter space, which is the two black hole masses and the two 3-dimensional spin vectors. There are two additional dimensions if you include eccentricity, but I'm going to neglect eccentricity because for almost all astrophysical binary black hole systems, by the time they enter the LIGO band and their gravitational waves can be detected by LIGO, they'll have radiated away all their eccentricity. So general relativity is scale invariant, so we can scale out the mass, which leaves us with a 7-dimensional intrinsic parameter space consisting of the mass ratio and two spin vectors. You'll note that in this figure I've drawn here, the two spin vectors are misaligned with the orbital angular momentum. So in this case, the orbital plane will precess as the binary evolves, and the spin vectors will also precess. So how do we measure the black hole masses and spins once we observe one of these gravitational wave signals? Well, here again, I'm showing you this plot of the residuals, which are consistent with detector noise. And what happened to get those is we subtracted the prediction of general relativity for one particular binary black hole system with some masses and some spins, and also the extrinsic parameters. So the binary was located in some sky direction and had some particular orientation. If you choose other parameters, you might also get residuals that are consistent with noise. And so the idea is that you need to check many predictions of GR and figure out a region in parameter space that is consistent with the signal that you've seen. So here we form this residual. Di is the data observed in detector I, and Hi is the prediction of general relativity for the data in detector I, given some parameters theta, where theta includes the masses and spins as well as the extrinsic parameters. And from this, you take an inner product, where this inner product is weighted by your detector sensitivity, and you get a likelihood function. So the idea then is to evaluate this likelihood function for many values of theta And here, many might be 10 million, it might be 100 million for a single gravitational wave observation. So this means we need to be able to make these predictions very quickly if we want to compute this likelihood for 10 or 100 million different parameters. So there's a problem in that we don't have a simple analytic solution to the two-body problem in general relativity. We don't have an analytic prediction for what LIGO should see in its detectors. So we have some very fast but approximate waveform models which can be used. So that's what was used in the analysis of GW 150914. There's these IMR phenom and EOBNR waveform models. And here we're looking at the posterior plot for the masses. And if we just look at the bottom, which is showing a one-dimensional posterior for the mass of the larger black hole, you see there's a red curve and a blue curve. And they agree quite well, but there is some slight difference. The width of this posterior is essentially determined by the detector noise and the signal-to-noise ratio of the event. So in the future, if we saw a much louder event, this width would get narrower. So for this particular case, the width is much larger than the difference between the blue and the red curve, indicating that the statistical error due to detector noise is much larger than the systematic error due to having a waveform model that's imperfect, assuming we can take the difference of these two curves as an estimate of the systematic error of the waveform models. For other areas in the parameter space, such as higher mass ratios and higher spins of the black holes, this might not be the case. It could be that the model waveforms disagree with GR predictions to an extent that's larger than the statistical error due to detector noise. This is very important if we want to do tests of general relativity. It's also very important if we want to get unbiased estimates of the parameters of the black holes. So we want a very accurate waveform model, especially for the future, where we will observe louder events. Okay, so I'm going to give you an idea of what these waveforms look like from binary black holes. So they look pretty simple in many cases. So this is face-on emission from a non-processing system. So face-on emission would be if the black holes are orbiting like this, and you are LIGO, and the gravitational waves are traveling this way. So there you see both polarizations, H plus and H cross, and you see they start out slow during the in-spiral, and they speed up, and at merger the frequency is much higher, and you get a peak in the amplitude, and then the remnant black hole rings down to a Kerr black hole. If you have edge-on emission, looks a little bit different, and you only get one polarization. Edge-on emission would be if the black holes were orbiting like this, and you are LIGO, and the gravitational waves are being emitted in the orbital plane. So what we typically do to describe the variation of the gravitational waves based on the direction of gravitational wave propagation is we put a big sphere around the system, and we look at the waveform all over the sphere and decompose it into spin-weighted spherical harmonics. So if we do this, I'm showing the L equal 2 modes on the bottom, and the black 2-2 mode is by far the dominant mode, along with the 2 minus 2 mode. If you look at L equal 3 modes, the 3-3 mode will be dominant there, but it'll be much smaller than the 2-2 mode. But you can see the blue here and the red, the 2-1 and 2-0 modes are much smaller compared to the 2-2 mode, although they're not completely negligible maybe at the merger. This was a non-processing system. In the diagram I showed you earlier with the spins misaligned with the orbital angular momentum, the orbital plane will precess, which means that this sphere and coordinate axes, set of axes we've chosen to decompose the waveform in is not necessarily the best choice at all times. So if we have a gravitational wave emitted in some particular direction, we'll get something like that on the top. You see there's a lot of amplitude modulation on the precession time scale. If we try to decompose it into modes like we've done before, we get this plot, and now you see the blue and the red curves are no longer negligible at all, even during the early in-spiral. So what we do for processing systems quite often is that instead of decomposing the waveform into modes in a fixed inertial frame, we choose a frame that is precessing along with the orbital plane of the binary. So if we do that, this precession looks something like this, where here we're representing the rotation from the inertial frame to the precessing frame as a unit quaternion. You see they vary quite slowly on the precession timescale, except at merger, where this precession timescale becomes comparable to the orbital timescale. But now if we do this mode decomposition, again, we recover approximately the mode hierarchy, where the 2-2 mode is by far the dominant mode, and the blue and red curves are much smaller. So how do we generate these waveforms? One method is a post-Newtonian expansion. So this is essentially an expansion in the speed of the two black holes divided by the speed of light, in some sense. So this is great when the black holes are far away from each other and orbiting very slowly. This fails completely near merger and becomes inaccurate many orbits before merger. So this particular method of generating waveforms is not great for binary black hole systems, where the merger will carry a lot of power in the detected gravitational wave signal. We can perform numerical relativity simulations. This is when we solve Einstein's equations on large computers by time stepping. So this can provide very accurate waveforms, but the problem is that it can take a week to a month to do one simulation on about 50 cores. So they're quite expensive, and that gives you maybe 20 orbits before merger. For some parameters, it may be even more expensive than that. So this is a great way of getting some very accurate waveforms, but if we need to evaluate those 10 million or 100 million waveforms for different parameters, we don't want to do that many numerical relativity simulations. There are some other models. The effective one-body model maps the two-body problem to a different effective problem and ends up finding waveforms that end up agreeing fairly well with numerical relativity, and they're designed to agree with post-Newtonian early on when post-Newtonian is good. They're then further calibrated to numerical relativity by adding in some free parameters and tuning them such that the waveforms agree with numerical relativity waveforms. This is one of the models that was used in the analysis of GW 150914, and it works pretty well. But if we want to go to very precise tests of GR and very accurate unbiased parameter estimates, we'll need a more accurate model, especially in certain areas of the parameter space. And improving this model by, let's say, an order of magnitude or two could be very costly and time consuming. These phenomenological models assume some fixed underlying structure of the waveform, maybe parameterized by frequency, and then use a whole bunch of free parameters that are fit to numerical relativity data. So this phenom P, which twists up a non-precessing waveform model using post-Newtonian expressions for precession, was also used in the analysis of GW 150914. So I'm going to talk about surrogate models. They're not an independent waveform model on their own, but the idea is that we take some waveform model that's already very, very accurate, but is too slow, and we evaluate it many times offline and try to interpolate the results in a very fast and robust way online. So the idea is to build a surrogate model of numerical relativity waveforms where we do a whole bunch of simulations right now, and as we start getting many, many LIGO detections, we can do fast parameter estimation in an online stage. So surrogate models have been built for other problems in gravitational wave research. First, they were built for effective one-body waveforms. The effective one-body model is reasonably fast, but not so fast that parameter estimation is a negligible cost. So you can speed it up by building a surrogate model, and some frequency domain reduced order models were also built. If you have a linear basis for your waveform, you can build reduced order quadratures and do very fast parameter estimation where you don't have to take so many inner products between your data and the predicted waveforms, which can speed it up by orders of magnitude. And surrogate models have also been built for binary neutron star waveforms, including tidal effects. So the advantages of using surrogate models are that they're fast and accurate, which is essentially what you want in a waveform model for doing parameter estimation or tests of GR. I've pretty much touched on all these points already, so I won't discuss them in detail. Okay, so now we're going to go through this toy problem where we're going to build a surrogate model for a very easy problem, and I'll go through the method. before we start applying it to gravitational waveforms which have some more structure. So the idea is we have some slow but accurate solution to some problem we want to solve, and we have plenty of time now. This says before signals arrive. Of course, 2 signals, maybe 3 have already arrived, but the signals are not yet arriving at a rate that's really great. We're not receiving 1 detection per week right now. So doing parameter estimation that takes a while is not too bad. And also, we don't have extremely loud signals yet. So doing parameter estimation with a waveform model that has some error in it is maybe not the worst thing. But later on, we'll need a more accurate waveform model that's also fast. So the idea is to evaluate this waveform model now many times and interpolate it in parameter space. So there are different ways you could interpolate in parameter space. One method you could use is just to compute the likelihood function where you have numerical relativity simulations already in parameter space. This would give you selected evaluations of the likelihood function in parameter space, and then you just interpolate that single function. This is an effective method, and it was used for GW 150914. It worked quite well. But in some cases, you do want to evaluate the actual waveform itself. The waveform has a bunch of structure, and you might be interested in measuring one particular part of that. Also, this method can be difficult to use if the likelihood function has many local maxima. So a naive approach would be to take all your numerical relativity waveforms, stack them up so maybe their mergers align, and then sample them on a dense grid of points. And for each particular time sample, you interpolate that the value of the waveform across parameter space at that time. So this would be quite expensive to evaluate online because you would need to do many, many of these interpolation steps. One for each time step you have. You might have 10,000 or 1,000,000 time samples depending on the length of your waveform. So the idea of a surrogate model is to just do a little bit better than that and to use the fact that you're not interpolating an arbitrary function, but you're interpolating a gravitational waveform, and we sort of know what those look like. So we can compress the data quite a bit to obtain a very sparse set of points in time at which we need to do this parameter space interpolation. Okay, so the toy problem we're going to look at is just some cosines plus noise, where here the noise comes in at the level of 10 to the minus 3. So here are 2 solutions. Here's time, which goes from 0 to 10, and our parameter space is lambda, which varies from 10 to 20. Here, lambda is controlling the frequency of the cosine. So the first step is to choose some particularly important values of lambda at which we need the solution. The idea is we want to build a linear basis using these particular solutions that's accurate enough to represent any function in our solution space to the desired accuracy. So we use a greedy algorithm where we start out with no greedy parameter values. So this would be n equals 0. Here we're showing the projection error as a function of parameter space. So the black curve n equals 0 has a very, very large projection error for all values of the parameter space, since currently our basis has size 0. Our projection errors are as large as they can be. We choose the value of lambda that gives us the largest projection error. And at this point, it doesn't really matter what value of lambda we choose, but we end up choosing this one over here just above 10. We add that solution to our basis. We perform a Gram-Schmidt orthonormalization, and then we repeat this. Yes?
You are restricting to a specific set of lambdas, or is lambda element R?
Specific set of lambdas, yes. So before you build this surrogate model, you need to define what your parameter space is, both in the time range and restrictions on how big the parameters can get. You could use all of R for lambda, but then you'd need an infinitely large basis to resolve all these cosines. So you usually need some parameter cutoffs, depending on how your solution behaves as the parameter goes to infinity. So with one basis element, we recompute the projection errors, and we get the red curve, which is now 0 at the particular value of lambda we added to our basis. It's large almost everywhere else. We repeat this process. The next point is here, and we find a whole bunch of different greedy parameter values, and we keep recomputing the projection error. You see the purple curve, the projection error is starting to get smaller. It's still touching that ceiling, but if we monitor the maximum projection error as a function of how many basis elements we get, we find a curve something like this. So the black curve is this reduced basis method I described. We start off with very large projection errors, but at some point we reach a saturation point where we start resolving the underlying structure of all our solutions, at which point the error decays exponentially until it reaches the error floor. So you can compare this with performing singular value decomposition, where you first evaluate your solution at all points in parameter space, take all your solutions and do a singular value decomposition and keep the first n of those, and you get a very similar curve. The singular value decomposition does a little bit better in terms of averaging out the noise up there, but they're quite comparable.
So
yeah.
Basically, greediness involves minimizing the transition value of that.
Yes. So the greedy part here is just you can think the problem here is trying to find a minimal basis which will represent our function space. A non-greedy algorithm would look at all possible combinations of all different values of lambda. Our greedy algorithm here is just given something that we think is a nearly optimal basis of size n, how do we find a nearly optimal size basis of size n plus 1? So we're not looking at all possible combinations of lambda. We're just finding the best choice for the next value of lambda and proceeding in this greedy way, and it does quite well. So the next step is to choose some corresponding empirical time nodes, some specific points in time at which we're going to do this parameter space interpolation. Now, we're going to use the fact that we can represent any of our solutions as a linear combination of the underlying basis functions. So if we have n basis functions, we're able to choose just n points in time at which we need to know the value of the function in order to recover the function at all other points in time. Specifically, so here's the parameter time plane. A solution in this plane is a vertical line, and these blue lines are the greedy solutions that we've identified. So suppose we want to know the solution at this cyan line where we don't necessarily have information. Suppose further that we are given the value of the cyan line at these cyan dots, at these 5 different empirical time nodes. I haven't told you how we choose the empirical time nodes yet. We'll get to that in a minute. But if you know the solution at these 5 points, you can decompose the solution into this linear combination of the basis vectors, and you obtain a system of n equations and n unknowns. You can invert it to find the basis coefficients, and then you plug that in to solve for your function at all points in time. So the fact that we can use a compact basis of, in this case, I think it was 42 elements to accurately represent our function space means we can choose just 42 points in time at which we need to sample the solutions. So how do we choose these points in time? Well, basically, this matrix here that we need to invert, or we need to solve this this system of equations, we want that matrix not to be singular. So this amounts to saying we don't want to choose 42 points in time that are right next to each other, because if you know the solution at one point in time, that's going to give you a really good idea of the solution at the next point in time. So we're again going to use a greedy method where we start with an interpolant that just returns the 0 function. And we're going to evaluate this interpolant on the next basis function we have. So here I'm assuming we've already chosen our first empirical time node. That's this black dot here. The function we're trying to interpolate is the solution at the second greedy parameter. That's the black curve. The blue dashed line is the interpolant evaluated at the second greedy parameter. And the red curve is the interpolation error. So you see the interpolation error is very large because we only have one basis element that we're using so far. We only have one empirical node. And we choose the next node to be this star where we find the largest interpolation error. We then attempt to interpolate the third greedy solution and repeat this process. Here we find the largest interpolation error over here, so we add that as an empirical time node. You notice, of course, at the empirical nodes, we get an interpolation error of 0 by construction. So as we extend this to the full 42, in this case, empirical nodes, we find that we can interpolate all the functions in our solution space with negligible error. And here, that interpolation error is shown as the dashed red line. The projection error onto the basis I was showing earlier is the black line. And you see we get some error amplification from basis projection errors to empirical interpolation errors. And that's basically related to the condition number of this matrix. So choosing these empirical time nodes to be, in some sense, far away from each other and independent keeps this error amplification small. If we had chosen other time nodes, this red dashed curve might be elevated even more above the black curve. Okay, so this gives us an empirical interpolant. It's called an empirical interpolant because it's data specific. So we can interpolate any solution in our function space. Really, we can interpolate any function that lies in the span of the basis we have. So here, g of t is just a very simple function that's just 1 everywhere. And if we try to interpolate this constant function, we end up with the red curve. So we do very poorly. And that's because the constant function does not lie in the span of our basis at all. So it tries to make it look like a cosine, and it does the best it can. So we sacrifice generality in this interpolation method, but what we get is a very sparse set of times. So our time sampling here is actually more sparse than Nyquist sampling. So if you're trying to build a general interpolant, it would fail miserably for this particular problem of cosines if you used only 42 time samples. So the
in the interpolation step now, if you want to interpolate a different lambda, do you have to invert matrices or?
No. So what you do when you build this empirical interpolant, you end up solving this beforehand. In the end, what you do is, in the end, you have a matrix multiplication. So you need to know the value of the solution at the empirical nodes, and you multiply this with some pre-computed matrix of new basis vectors. And these new basis vectors are the empirical interpolant basis vectors, which are different from the orthonormal basis vectors you've constructed before, but they're a linear transformation of them.
And you can compute them ahead of time?
Yes. Yep. So the final step is we needed to know the value of this new solution at the empirical nodes. So we need to figure those out, and that's basically what we've reduced the problem to. So the black curve, for example, is the value of the solution at the first empirical node as a function of parameter space. So we need to build parameter space fits or interpolants or whatever we want to come up with a model of these. In the end, here's a diagrammatic representation of our surrogate model. If we want to predict the solution at this particular value of lambda where we had no previous information, what we first do is at each of these red lines, we interpolate or fit the black dots across parameter space and evaluate the solution at this cyan dot using our fit. We do this for all the red lines, and that gives us the value of the solution at the empirical nodes. Then we use the fact that the whole cyan line is a linear combination of the blue lines. We do this empirical interpolation, and we recover the solution at all times. Okay, so that was the toy model. If there are any questions about the method, I'll take them now. Otherwise, I'll jump into the gravitational wave surrogate models. Okay, so the first surrogate model we built, using numerical relativity waveforms, we wanted to do a simple test case as a sort of a proof of principle to show that we could build very accurate surrogate models for gravitational waveforms. So we restricted to a one-dimensional subspace of the parameter space where only the mass ratio varies and the black holes have no spin. So we ended up doing 22 numerical relativity simulations using the spectral Einstein code. And they're all the same length in time. And we build models for all the spin-weighted spherical harmonic modes that the code could resolve. And our surrogate model then takes about 10 milliseconds to evaluate on a single core, to evaluate all of these modes. That's compared with a week or a month maybe to run a new simulation using the spec code. The important thing in this study was that we were able to produce surrogate model errors that were comparable to the underlying resolution errors of the numerical relativity simulations. So in some sense, this surrogate model has converged to the underlying solutions, and we can't hope to improve the model any further unless we do more accurate numerical relativity simulations with higher resolution. So how did we choose the mass ratios for these 22 points? In the toy problem, we evaluated the projection error at all possible values of the parameter space. Of course, we don't want to do numerical relativity simulations at all possible mass ratios because that would defeat the purpose of what we're trying to do. So instead, what we did is we chose these greedy parameters using a different waveform model. We used effective one-body waveforms. And so this model was used purely to determine these greedy parameter points. Now, of course, if we used actual numerical relativity or general relativity predictions, we would have obtained slightly different mass ratios. And maybe by the time the errors start getting small, we would have obtained very different mass ratios for these greedy parameters. But the idea is that this approximate waveform model should be good enough to give us a good indication of roughly how the waveforms vary as you vary the parameters, and give us a good idea of the distribution of points we should use. So in the end, what will happen is our set of mass ratios won't be optimal, but it will be close to optimal. So in the end, all we need to do is include a few extra mass ratios that maybe we wouldn't need to otherwise use, and we'll have an accurate enough basis. So we did these simulations and looked at the data. Here on the top are the amplitudes of the dominant 2-2 mode. So here's the merger where the amplitudes peak. And this is the in-spiral. So the black curve is equal mass, and the red curve is mass ratio 10. These are the two extremes of our parameter space. And these x's with the lines going through them are the empirical time nodes that we found. So at each of these empirical time nodes, we're going to do a parameter space fit. You see, most of them are here at the merger and the ring down, where most of the where things are changing the most. And we don't have many points during the early in-spiral where things don't change very much. On the bottom, we have the phases of this dominant 2-2 mode. The waveforms were all aligned at the initial time, so they were rotated such that their phases were 0. And we find we don't get a time node until here, about halfway through the in-spiral. We then get another one here just before merger, and then the remaining 20 points are here during the ring down. This makes sense because at the ring down, the amplitude is very, very small, meaning these phases are becoming poorly defined and the numerical resolution errors get amplified and we get very large errors there. So different methods could be used to try to overcome this, and we could use, instead of choosing the point with the largest empirical interpolation error, we could compare the empirical interpolation error to the intrinsic error in these simulations and the resolution. And so the phase errors at ring down would be very large, and we would maybe not pick those points. We found that it didn't matter so much. This worked reasonably well, so we didn't bother trying to improve on it. So let's look at the parameter space fits. Yeah?
Going back to that.
Yeah.
It almost looks like if you just don't care about ring down and you ditch it entirely, you could fit the phase with 3 points all the way through merger.
Not quite. Almost. Yeah. So are you asking what happens if we just throw away this?
Well,
or,
I need 1 point to anchor it.
Okay. Yes. Yes.
But if I threw away all the other
okay.
ones, would you be able to do? Because that's,
probably.
That's
yeah.
That's all in the signal there.
Yeah.
Right?
Yeah.
Ring down doesn't do anything.
Right. Yes. If you threw away all these points and tried to interpolate it, you'd probably do pretty well.
Does that say something about it?
It says that the phases are pretty simple and for non-spinning binary black hole systems, yeah. They're not too complicated. It could be that you'd need at least 2 points here to try to get the ring down frequency. So it could be you need 4 or maybe even 5 points. Yeah.
What are the basis functions you're using to interpolate between?
So to interpolate in time,
Yeah.
so those are the empirically found basis functions. So we take all of these solutions and we build a reduced basis from it. Basically, the solutions are the basis.
Numerical solution.
Yes, yes.
And don't the points at the very end of the ring down also contain information at
Yes, yes.
So if you remove those and just try to fit
Yeah, so if you completely removed all of these points and tried to do the interpolation, it wouldn't be accurate. If you included one point here to anchor it, as Aaron mentioned, my guess is that that would probably be pretty accurate, but maybe you still get some extra information. What you really want to do, if we had to go back and do this again, is we would take our 22 solutions, and now we wouldn't build a reduced basis, but we would do singular value decomposition. We would look at that projection error versus number of basis element plot, and it would probably look something like this, where it decays exponentially at first and then levels off once you hit noise. And we basically would just ignore all those noisy singular values and just use the ones that actually matter. In this case, you would probably get a basis size of 3, is my guess. Maybe you would need a basis size of 4, potentially even 5. But then if you're only choosing 4 or 5 empirical nodes, you're not going to get 20 of them during the ring down. So that would be one way to get around this. And that would speed up the model, so that would help. And we do this in later surrogate models. So the parameter space fits are pretty easy in this case. Here we're looking at symmetric mass ratio. So over here at 0.25 is equal mass, and over here is mass ratio 10. So on the top again we have the amplitudes, and they're almost linear, and we end up using 5th degree polynomial fits in the symmetric mass ratio, and it works really well. For the phases, you see this black curve has a lot of noise, and that time is 100 m after the peak amplitude. So that's the very last time sample right here of the ring down. That's where the phases are the worst defined, and there are large errors, but we get an okay fit. So evaluating this, this surrogate model and comparing it to the numerical relativity waveforms, we find what the errors are. So we're able to estimate the resolution error of the numerical relativity waveforms by comparing waveforms that use different resolution for the simulations. Those are these black dots here, and you see the largest one is up here, around mass ratio 3 or so. If we just evaluate the surrogate at the particular mass ratios we use to build it, and basically spit out the input waveforms and reproduce what was input into the surrogate, we get these red squares. Those aren't a very good estimate of the surrogate's ability to interpolate to new parameters. So to do that, we do a cross-validation study, in particular a leave one out cross-validation study, where we get the blue triangles. And these are computed by, for each mass ratio, you build a trial surrogate that's built from the waveforms at all other mass ratios, but you neglect the one at that particular mass ratio. You then evaluate the surrogate at that mass ratio and compare that surrogate evaluation to the numerical relativity simulation. And so these blue triangles, the largest blue triangle is similar to the largest black circle, so we conclude that our model is doing about as well as it can because its largest errors are similar to the largest errors of the input waveforms. If we look at the worst surrogate case and actually look at the waveform, this is what we get. In blue is the spec numerical relativity waveform, and the dashed red line is the surrogate evaluation. They lie on top of each other. If we look on a log scale and look at the errors, the black curve is the amplitude of the waveform. The dashed red line is the numerical relativity resolution error, and the solid red line is the surrogate error. This was this leave one out cross-validation study for mass ratio 2, which gave the largest surrogate error, and you can see the two red curves are very similar, indicating we're doing about as well as we can. It's very easy to evaluate this model. I'm going to skip through this in the interest of time, but if you want to download it, come see me. And you can evaluate it using a simple Python interface called GW Surrogate. Okay, so that was a case that worked very well. We did as well as we could. The problem was it's a very simple one-dimensional subspace of the parameter space. We really want to go to this 7-dimensional full parameter space so we can do proper parameter estimation. Doing that jump from 1D to 7D seemed daunting, especially since we would need to do thousands of numerical relativity simulations. And we had just heard the news about GW 150914, and we thought, hey, let's do something quick. So we restricted to a 5-dimensional processing parameter space. The restriction here is that the spin on this smaller black hole is initially aligned with the orbital angular momentum. As time goes on, the system will process, and so this will no longer be the case at later times, but we end up with a 5-dimensional subspace. We're also restricting to mass ratios between 1 and 2. This is pretty much appropriate for GW 150914, and we did this essentially because numerical relativity simulations become very expensive at high mass ratio. Yeah.
What is initially here?
Initially is after junk. Initially is actually 4,500 M before the peak amplitude. So setting the spins to be exactly aligned is not really doable because you can't predict the exact length of the simulations, but they're quite approximately aligned because they change sort of on the precession timescale, other than some orbital mutation things. So we did 275 new spec simulations for this parameter space. This surrogate model uses longer waveforms that have about 20 orbits before merger. Unfortunately, we actually tried to use a 4-dimensional subspace. We tried to also restrict the azimuthal angle on the spin of the larger black hole. We wanted it to be initially 0. This would give us a 4-dimensional subspace that would be easier to model. The problem is that to determine that angle, we need to predict the length of our simulations until merger. And our way of doing that is just using post-Newtonian expressions, which have large errors. So we end up with all sorts of azimuthal angles. This is a problem because the azimuthal angles we obtain are highly correlated with the other parameters we have. So we're unable to do parameter space fits in this additional dimension. So what we end up doing is we use an analytic approximation for the dependence of the waveform on this azimuthal spin angle. And this approximation works very well during the in-spiral. It's exact for orbit averaged post-Newtonian equations. But unfortunately, it fails during merger, and so we introduce a bunch of additional waveform error because of that. So to choose the parameters, we did a similar thing to before, where we use a different waveform model. In this case, we use post-Newtonian waveforms. So here's the projection errors we got. It's very noisy due to random sampling. We did this very quickly, and it reaches an error floor because I restricted the parameter space fits to have a fixed number of coefficients, and to go further, they would need more coefficients. But the key thing here is that to find the points in parameter space, we couldn't just look at the basis projection errors. We had to build entire post-Newtonian surrogates, and that's because the basis became very accurate with about 30 waveforms and 30 points in parameter space, which is great to have a very compact basis because it means our model will be very fast to interpolate. The problem is that we can't do these parameter space fits in 4 or 5 dimensions using only 30 points. So we built post-Newtonian surrogates, found where the surrogates did the worst, and added those points to the surrogates, and continued until we had about 275 points. And we did those simulations. So these precessing waveforms look a lot more complicated. For the non-spinning case, you saw we used the amplitudes and the phases, and they worked really well. Here you see the amplitude of the 2-2 mode in red is very wiggly, and building a model for this is going to be very difficult, especially since these orbital timescale oscillations are very parameter dependent. They'll be at different frequencies for different parameters and different amplitudes as well. Also, if we look at the 2-1 mode in purple here, we of course have these amplitude modulations. And so we'll end up with a very large basis and very difficult parametric fits if we try to build surrogate models for these components. So what we end up doing is a big waveform decomposition into simpler pieces. So the first step is to go into this co-processing frame that I mentioned at the beginning of the talk, where we're in a frame which processes along with the binary black hole system. In this frame, the modes look a lot more simple. The black and red curves are the amplitudes of the 2-2 mode and the 2-2 mode. You see they're a lot smoother than in the previous plot, but there's still some little orbital timescale oscillation. And this is maybe small during the in-spiral, but at merger, the difference between the black and the red curves becomes quite significant. So we want to model this behavior, but again, we don't want to have to model these oscillatory pieces. So what we do instead is we look at the symmetric and anti-symmetric components of the black and the red curve. So if you take the average of the black and the red curve, you get something that's very smooth and looks like a nice smooth amplitude that through merger is smooth as well. If you take the symmetric difference, you end up with a real oscillating part. That's not actually what the purple curve is, but it looks similar to the purple curve. And what we then do is we take a Hilbert transform of that real oscillatory piece to end up with an amplitude in phase. The Hilbert transform essentially gives you the imaginary part. If you have a real sinusoid, it will give you the cosine in some sense. So we do some more data decomposition. Of course, we need to now model the precession as well. So we can take this waveform in the coprocessing frame and use our knowledge of the precession to transform it back into the inertial frame. So in terms of unit quaternions, the precession looks sort of like this. It changes very slowly during the in-spiral, and then at merger it gets a lot faster. These are still oscillating components that will depend a lot on parameter space and will oscillate at different frequencies. So we don't like that so much. We want to get some kind of phases. So we do a further decomposition on this. We do filter out a little bit of this precession. If you zoom in very closely on these things, they do oscillate on the orbital time scale. This filtering results in a negligible error when we reconstruct the waveforms, though. So what we end up with is two phases. The top one is a precession phase that gives us the total length on the unit sphere of the trajectory traced out by the z-axis of this, or z-axis, sorry, of this coprocessing frame. It's sort of the total amount of precession. And you see it looks a lot like a phase. You know, at merger it speeds up, and at ring down it's very fast. And the red and the black curves are before the filtering and after the filtering. So in this case, it doesn't affect it all that much, except at a ring down. And then the other thing is we need to know the instantaneous direction of precession. So in this coprocessing frame, the direction is always in the xy plane. And so if we look at that direction over time, it will trace out some curve, and we look at the phase of that, and we get these red and black curves here. Again, the red one is after filtering, and here you see there's a lot of oscillation, and that's why we did the filtering in the previous step. So that also looks like a phase, and it's not too difficult to model. We also do some other things with different modes, but in the end, we get a very complicated decomposition diagram. Don't worry about what all the pieces are, but in the end, we take our waveform and we drop it down the diagram, and we get these different pieces, and for each piece, we build a separate surrogate model. And to evaluate the surrogate, we evaluate the surrogate models for each piece and build everything back up the diagram to get our waveform. We then do the parameter space fits. We use basis functions in each parameter space direction. I won't bore you with that. Let's just jump to the errors and see how we do. So in red is a histogram of the mismatches, which is some error measurement that's similar to an L2 error squared. So it's the red curve is for the numerical relativity simulations. So typical mismatches there are about 10 to the minus 5. They're very accurate. The surrogate model errors are in blue and green here, and they're typically about 10 to the minus 3. So in this case, we did not manage to achieve similar errors to the resolution errors in the numerical relativity waveforms that were used to build the surrogate model. This is mostly because of the fact that we weren't able to resolve this azimuthal angle on the spin of the larger black hole. So in order to fix that, we could do additional simulations that vary this azimuthal angle. And instead of using this analytic approximation for that parameter, we could do the parameter space fits directly. But we do manage to do better than other waveform models. So the cyan and purple curves are these SCOB and RV3 and phenom P V2 curves, which are used by LIGO in gravitational wave parameter estimation. So they have typical mismatches of 10 to the minus 2 when we look in this region of the parameter space. So we do about an order of magnitude better than them. Sorry?
What are you aiming for?
That depends on the signal to noise ratio of the signals we see. So one thing you can do is if your whole error curve is less than this relevant SNR, you're guaranteed that your systematic error in your waveform model is not going to affect any analysis because it's much smaller than the statistical error due to detector noise. It's a sufficient but not necessary bound, and it's fairly pessimistic. So this seems to indicate that even at signal to noise ratio 10, these waveform models wouldn't be appropriate, but really they are.
But, okay, suppose you want to measure spins to pre-merger spins to 10%? Or that's a market?
More than 100 for sure, maybe 300. Spins to 10% would be hard. Yeah, maybe 10 years from now we can do that. So there maybe we would even need to do some, yeah, there maybe we would even need to improve the numerical relativity simulations and do higher resolution. But for now, mismatches of 10 to the minus 3 is quite good. The problem is this is a very restricted area of the parameter space, and getting mismatches of 10 to the minus 3 at higher mass ratios might be very hard. So I think, what's the time like? I think I'll end there and ask for questions. But here are the next steps. We plan on extending this to the full 7-dimensional parameter space. Then we won't have this problem with the azimuthal angle because all parameters will lie in our space. We won't have to worry about initial conditions. These waveforms are also of finite duration, and LIGO may see some very long signals that include a lot of the early in-spiral. So to make our surrogate models suitable for that, we would need to extend the length. Doing longer numerical relativity simulations would be possible, but costly. So instead, we plan on hybridizing the output of the surrogate model with post-Newtonian or effective one-body waveforms, and then building a surrogate model for these hybrid waveforms. So we can stack surrogate models on top of surrogate models to add extra length to the waveforms, and this can also improve the speed of the surrogate model. We also want to go to higher mass ratios. Of course, mass ratio 2 is very restrictive. Eventually getting up to mass ratio 10 or so would be great. And we're also currently restricted to spins of 0.8. So extending to higher spins would be good. But I'll end there and take any questions you have. Thank you.
No, I didn't have a question. I was going to ask you.
Okay.
Well, the updated version of Spec, the GR solver, will that make it easier to do high spins? I'm just curious.
The Spectre?
Or is it more you combining with high
Spec can
spins?
already do high spins.
Yeah.
It may make it faster, the local time stepping and those things actually.
So Spec can do spins above 0.99. They're just very, very slow.
Exactly.
The
speed up really matters.
Yeah.
So for the restricted parameter space, I can see how it's kind of an obvious first step when you have to run the simulation from an initial setup, right? Freeze one of the spins, try to minimize the other one, and then step simply. But it doesn't seem like it has much to do with sort of a physical cut of the 70 parameter space, right? So you're sort of randomly picking phases in the spin directions. So is there a reasoning for what was done, and is there something you can do that maybe reflects better the angles and choices in, say, piano precession analyses, where there are particular angles that really have physical importance?
Yes. So there was a little bit of physical motivation for this choice. The Phenom P model has explored a very similar parameter subspace extensively. So it uses, in terms of precession, it uses one effective precessing parameter, and it essentially places all of the in-plane spin, so the spin orthogonal to the orbital angular momentum, in this effective precession parameter, which is then placed on a larger black hole. So we chose this because that had been shown to work pretty well. In hindsight, it maybe would have been better to, for surrogate modeling purposes, to choose a 4-dimensional space where we have no spin on the smaller black hole and arbitrary spin on the larger black hole. This would have been a lot easier to model, and we wouldn't have run into this issue with the azimuthal angle. The problem with that is that the phasing contribution from the spin on the smaller black hole, especially since we're at nearly equal mass, can be one of the leading contributions to the waveform phasing. So mass ratio is probably the most important, and then the aligned components of the spins. So there was a big press to have both aligned components of the spins in the surrogate model.
how many simulations for a 70 processing surrogate?
Right. So we've run something like 400 or 400 to 500 new simulations that are almost all finished, and this is for an extension of this mass ratio 1:2 case to the full 7-dimensional processing parameter space, and we think that should be enough for this very restricted mass ratio less than 2 case. Yeah. So of course you would expect it to scale exponentially in the dimensionality of the space. We're hoping to make use of the fact that certain parameters matter a lot more than others, and if we can come up with a very good parametrization of the space, we should be able to use very low order basis functions for the fits in certain dimensions of the parameter space. So it's possible that we won't, I'm guessing we won't recover the resolution error of the underlying numerical relativity simulations with this many parameters. But I also think that we can build a model that will be better than existing models within this space. Of course, going to better accuracies is just a matter of running more simulations then. Yeah.
Can you comment on your last bullet? What needs to be changed towards test particle?
Yeah. So if we looked back, all the way back at, let's say, where was it? Here. So if we're doing these fits in terms of symmetric mass ratio, if we look at the amplitude of the 2-2 mode, we know that in the test particle limit, the amplitude is 0. So we could anchor these fits by including a point at 0. Now, for the phases, this doesn't work too well because these phases will dive down like that as you go to 0. So this isn't a good parameter. So using phases is not a good way of being able to anchor these fits. The idea is that if we anchor the fits, we'll be able to extrapolate a little bit with higher accuracy. And we can test how well we're extrapolating by performing some extra simulations. So parametrizing not by the phase, but maybe by, in a post-Newtonian-like way, where we parametrize by the orbital frequency and we model the time derivative of the orbital frequency.
That seems dangerous because you know there's going to be some kind of turnover in the behavior as you move away from equal mass to extreme mass. And so I would think that if you didn't include at least 2 points, or maybe more, near the extreme mass situation, you're going to hit 0, fine, but you're going to come at it with the wrong slope and potentially really damage your curve.
True. So if we can use some self-force results to determine the slope of, and also anchor the slope here, that would be really useful. And that could really improve things. I think for the amplitudes, should it just hit 0 in a linear way? I think I
think for amplitude it's scaled with mu.
Yeah.
Right? So that you may already know the answer.
That one's
there.
maybe easy. Yeah. But if we could get the right slope for this linear thing, that could help the extrapolation quite a bit.
I can see why you would want to be more ambitious in extending the mass ratio, but then that's going to cost you a lot, covering more parameter space. So does this bring in considerations of what mass ratios, for example, are likely to be produced in nature and what mass ratios are likely to be detectable? It must actually go down.
Yes. So if you had, it might be very unlikely for LIGO to detect, let's say, a mass ratio 100 merger, both because these are less astrophysically expected and because the amount of gravitational radiation produced from such a system wouldn't be as visible in LIGO. So, I mean, yes, of course. So eventually, we would want to be able to detect these accurately in case we see them, because they would be extremely interesting. But we have seen a couple signals so far, and they've been closer to equal mass. And so maybe we expect that most of the signals we would see in the near future would be around there. There could be. So it could be that if waveforms are sufficiently inaccurate in some area of the parameter space, it could be that current searches aren't effective enough. But my guess is that if searches aren't accurate due to waveform error, we'll still be able to see very, very loud events with these searches. We just might be missing, if we were missing anything, we would be missing just barely above threshold events. So yes, maybe doing better in a somewhat restricted area of mass ratio would be more economical and provide the most value for the near future.
I have a question as well. So on that same note,
Yeah.
So as you increase the mass ratio, you would presumably be more likely for the lighter thing in your simulation to have some matter effects. Right? So if you have some decent, like 20 solar mass black hole and a normal neutron star, then how do you know how accurate or like how well your just black hole surrogates would be able to do for that?
Right. So far we haven't looked at modeling the effects of matter. Ben Lackey et al. have produced surrogate models including tides. So we could consider including tidal terms as an additional parameter in the surrogate model. I'm not sure, I guess I'm not sure how inaccurate we would be in terms of black hole neutron star mergers. It probably depends on the mass ratio. Maybe at nearly equal mass, if you had one, or closer to equal mass, if you had one neutron star and one black hole, you might get a lot more disruption, and this could change the waveform a lot more. Whereas if you had larger mass ratios, maybe the neutron star just gets swallowed up, and maybe the tidal terms are less important. But so far, I've only looked at binary black holes.